All right, let's look at another quantity that's measured on a logarithmic scale. Here we have the pH of different chemicals. Chemists measure the acidity of a solution by measuring its hydrogen ion concentration using the following metric. The pH equals the opposite of the logarithm of H plus, where H plus is the concentration of hydrogen ions measured in moles per liter, capital M. The reason we have brackets around H plus is because H alone means hydrogen and H plus means hydrogen ions, but if we want to look at the concentration, we use those brackets to refer to that. So this is just a notation that we use because we're dealing with the concentration of something in chemistry. Anyways, this was done to avoid very small numbers and negative exponents. Solutions with pH less than 7 are acidic, and solutions with pH greater than 7 are basic. Notice, again, because this is a logarithmic scale, that when the pH increases by 1 unit, the hydrogen ion concentration decreases by a factor of 10. Decreasing, of course, because we've got a negative in front of that logarithm. So this is how the acidity is measured with pH. Let's take a look at a couple of problems. First, we note that the hydrogen ion concentration of a sample of human blood was measured to be 3.16 times 10 to the negative 8 moles per liter, which we'll use in the first part of the problem. Find the pH and classify the blood as acidic or basic. So here, the pH is equal to the negative logarithm of the hydrogen ion concentration. And in this case, that is 3.16 times 10 to the negative 8. So we need to take the opposite of the logarithm of 3.16 times 10 to the negative 8. And we're actually going to use the laws of logarithms here to break this up. We know that the logarithm of a product is equal to the sum of the logarithms. So this is going to be negative log of 3.16. And I'm going to write minus because even though this is the sum, we've got a negative out front that gets applied to both of them. So this will be minus the logarithm of 10 to the negative 8 power. And we can use another law of logarithms here. We can bring the exponent out front. When we do that, we've got negative log of 3.16, and then it's going to be plus 8 times log of 10, because we're subtracting and we pull out a negative 8, and subtracting a negative is the same as adding. And now log of 10 is just 1, because 10 to the first power is 10. So this is just 1, and 8 times 1 is just 8. So we've got negative log of 3.16 plus 8. And now we can use a scientific calculator to get an approximation of this other logarithm. And when we do that, we end up with a pH of approximately 7.5. So we have found the pH of blood. And when the pH is greater than 7, it's classified as basic. So this blood is basic. It almost sounds like an insult. That blood is basic. But it's not. I hope I made you laugh. If I can make you laugh once over the course of the semester, I have done my job. If I can make you roll your eyes, even better. All right. Next, let's look at the other question. What is the hydrogen ion concentration of household bleach, which has a pH of about 12.6? In this case, we know the pH, 12.6, and we need to find the hydrogen ion concentration. So we substitute in 12.6 for the pH in the formula for the pH, and we need to solve for the hydrogen ion concentration. Whenever we're solving for a variable inside a logarithm, we want to isolate the logarithm first and then put it in exponential form. So first we want to get rid of this negative sign out front. If we divide both sides by -1, this should give us negative 12.6 equals the logarithm of the hydrogen ion concentration. And then we can write this in exponential form. This becomes 10 to the negative 12.6 equals that concentration. And if we type this into a calculator, I know with my calculator, I get an answer in scientific notation. So when I do that, I get that the hydrogen ion concentration is approximately 2.51 times 10 to the negative 13th power. If your calculator says something like E negative 13 or E minus 13, that means times 10 to the negative 13th power. So this is a very, very, very small number. It's less than 1/billionth. And so because of that, it's generally useful to write it in scientific notation. And this is measured with moles per liter, so capital M. And so this is our concentration of hydrogen ions in household bleach. Just one very quick note, the reason why this is a logarithmic scale is because if it wasn't, if we had just looked at the concentration of hydrogen ions, we would have numbers that are so tiny, our brains wouldn't really know how to process them. And so by turning it into this logarithmic scale, we end up with numbers that are much easier for us to deal with. The pH scale runs from 0 to 14, with 7 being neutral, and those numbers are all much easier to work with than 2.51 times 10 to the negative 13 power. So logarithms can be very, very useful for us when we're dealing with tiny, tiny, tiny numbers, like in this situation, or giant, giant, giant numbers when we're looking at earthquakes with magnitudes in the millions or more.